do the rest.
Okay, so hi everyone, I'm Zhang from the Hong Kong University of Science and Technology. I'm pleased to welcome you to my presentation. In this presentation, we will explore how combining the strengths of transformers and graph neural networks can significantly enhance the capabilities of recommender systems. So let's get started. We will start with some context about the current landscape of recommender systems. We'll then identify the key challenges faced by existing methods. After that, we'll delve into the core of our approach and evaluation. Finally, we will summarize our findings and discuss the implications of our work. So for the traditional recommender paradigm, which primarily focuses on the interaction between instances while often ignoring the connection between them, this approach can lead to what we call the information isolated island effect. This isolation can result in several issues. When an instance representation depends solely on its own features, it fails to capture the broader context and connections that would enhance its representation. And by overlooking the relationships among instances, the model struggles with sparse data issues, where interactions between users and items are insufficiently captured. Overall, the model's capacity to learn and predict effectively is hindered by such isolated approach. To address the limitations of traditional recommender paradigms, one effective solution is to reorganize the data into graphs. By doing this, we can tackle the issue of limited representation ability through information propagation along the connections between instances. This allows the model to capture and utilize the relational dynamics that are often overlooked in isolated approaches. Additionally, this reorganization enhances the model's capacity. By leveraging high-order connectivity, we can complement the user-atom interactions with richer, more interconnected data. Now, let's delve into the graph-based collaborative filtering. Collaborative filtering is based on the homomorphy assumption, which suggests that a user's preference can be predicted from those of similar users. This means that collaborative signals, such as user behaviors and interactions, can be used to infer behavioral similarity among users. Graph-based collaborative filtering takes this concept further by leveraging graph structures. It models collaborative filtering with high-order connectivity through the use of graph neural networks. Despite the effectiveness of the existing graph-based collaborative filtering models, several fundamental challenges still remain unsolved. Firstly, the message passing mechanism relies on edges to fill the graph structures and node attributes, leading to strong bias and potential noise. For example, recent studies on eye tracking demonstrate that users are less likely to browse items that are ranked lower in the recommended lists, while they tend to interact with the first few items at the top of lists, regardless of their relevance. Therefore, the topological connections within interaction graphs are impeded by the aforementioned positional bias, resulting in less convincing message passings. Worse still, the propagation of embeddings along edges can amplify noise effects, potentially distorting the encoding of underlying user interest in graph-based models. Secondly, the reset fields of GNNs is also constrained by the challenge of oversmoothing. It has been proven that as the GNN's architecture goes deeper and reaches a certain extent, the model will not respond to the training data, and the node representations obtained by such deep models tend to be oversmoothed and also become indistinguishable. Consequently, the optimal number of layers for GNN models is typically limited to no more than 3, where the models can only capture up to 3 hop renditions. Therefore, in real-world applications, due to the inherent constraint of the network structure, GNN-based models struggle to capture such long-term sequential information. Fortunately, the transformer architecture can globally and adaptively aggregate information with the self-attention module. However, their ability to effectively utilize graph structure information is constrained because the aggregation process does not rely on edges. Moreover, the computational complexity of attention calculation scales quadratically, becoming impractical for large-scale recommender systems. In addition, under the global attention setting, irrelevant user-atom interactions are also incorporated, leading to suboptimal performance. Therefore, we inquiry Whether the integration of transformers and GNNs can leverage their respective strengths to mutually reinforce each other. By leveraging transformers, the receptive field of GNNs can be expanded to encompass more relevant nodes, even those located distantly from central nodes. Conversely, GNNs can assist transformers in capturing intricate graph topology information and efficiently aggregating relevant nodes from neighboring regions. Then we'll introduce the method called TransGNN. Here is the framework. We first sample the most relevant nodes for each central node by considering the semantic similarity and graph structure information in the attention sampling module. Then in the positional encoding module, we calculate the positional encoding to help the transformer capture the graph topology information. After these two modules, we use the TransGNN module, which contains 3 submodules in order: the transformer layer, GNN layer, samples update submodule. As we have discussed that the computational complexity of attention calculation scales quadratically, and under the global attention setting, irrelevant user atom interactions are also incorporated, leading to suboptimal performance. So we argue that it is unnecessary to compute attention across the entire graph for each node. Instead, prioritizing the most relevant nodes is sufficient, thereby reducing computational complexity and eliminating noisy node information. So we commence by computing the semantic similarity matrix, and we update it to include the structural information. Then for each central node, we sample the most relevant nodes for it. So unlike the grid-like data where the sequential patterns can be easily captured by a transformer, interaction graphs present a more challenging topology to navigate. To enrich transformers with this topological knowledge, we introduce 3 distinct positional encodings tailored for recommendation scenarios: the shortest path hop-based positional encoding, the degree-based positional encoding, and the PageRank-based positional encoding. The first 2 encodings signify the proximity between users and items, emphasizing the diversity and frequency of user interactions or the popularity of items. Meanwhile, the last encoding indicates the significance determined by the graph topology. By aggregating the above encodings with raw user item attributes, we enrich the transformer's understanding of the recommendation landscape. So the TransGNN module synergizes the strengths of GNNs and transformers to alleviate their own weaknesses. This module consists of the transformer layer, the GNN layer, which are combined in sandwich style, and the samples update submodule. Among them, the transformer layer is used to expand the receptive field of GNN layer and aggregate the attention sample information efficiently, while the GNN layer helps the transformer layer perceive the graph structure information and obtain more relevant information of neighbor nodes. The sample update submodule is integrated to update the attention samples efficiently, where we adopt 2 strategies to update the attention samples. The first one is the random walk-based, where the random walk transition probability is utilized, calculated as follows. And we also try the message passing-based attention sample update. So here we demonstrate the expression power of TransGNN. We have the first theorem that TransGNN has at least the expression ability of GNN, and any GNN can be expressed by TransGNN. If we add attention mask as top one mask, the equation of transformer layer will become the following equation. And we use the GCN layer as an example, and the message passing can be derived as follows. Here, sigma is the activation function. If we set the W matrix as a diagonal matrix with the diagonal values at the squared output dimension -1, then the above equation will become as follows. Therefore, TransGNN has at least the expression ability of GNN. And next, with the help of transformer layer and positional encoding, TransGNN can aggregate more relevant information and structure information to improve the message passing process, which can be more expressive than the first WL test. We give an illustration in this figure. And these two graphs cannot be distinguished by the first WL test. However, because the transformer layer expands the reset field and the positional encoding can capture the local structure, they can be distinguished by TransGNN. For example, in the blue node in the top left gets the shortest path information towards other blue nodes with 0, 1, 3, 3 for the left figure and the 0, 1, 2, 3 for the right figure, respectively. Next, we'll show the experimental results. The data sets used in the experiments are shown in the tables. We adopt the 5 widely used benchmarks. And we compared with the autoencoder-based baselines, the GNN-based baselines, the hypergraph-based baselines, the self-supervised learning-enhanced GNN-based baselines, and the hypergraph transformer-based baselines. And we find that GNN-based methods outperform autoencoder-based methods. The hypergraph neural networks outperform many traditional GNN-based methods by capturing high-order and global graph connectivity. And our TransGNN achieves competitive performance compared to other baselines. Here is the evaluation study of TransGNN. We find that removing the attention sampling module leads to a noticeable performance decline across all data sets, and excluding the positional encoding module compromises results, and removing individual components further degrades performance. The simultaneous need for both transformer and GNN layers is evident, as removing either significantly declines performance. Here is the attention sampling study. As the attention sample size K increases from 5 to 35, a trend is observed where fewer nodes reduce computational load but degrade performance. This decline is due to insufficient nodes capturing essential user-atom connections, impacting the model's accuracy in recommendations. Conversely, overly extensive node sampling fails to proportionally enhance performance, indicating a saturation point where extra nodes add computational strain without improving predictive accuracy. We adjust the graph scale to identify the optimal sampling size. Interestingly, we find that a relatively small sampling size is found to be sufficient for achieving good performance. This finding suggests that TransGNN can operate efficiently without necessitating extensive computational resources. And the ability to extract meaningful insight from a smaller subset of nodes underscores the effectiveness in identifying the most pertinent information from the user-atom interaction graph. And when the graph size is varied, we observe that only a slight increase in sample numbers is needed as the graph expands, indicating TransGNN's scalability. Despite increasing graph complexity, the model does not demand a large increase in resources to sustain performance. This scalability is essential for practical applications with large and varied dataset sizes. At last, let's make a recap to my presentation. For the challenges in graph-based collaborative filtering, the bias and noise in message passing, we perform attention sampling to keep relevant nodes. And for the failure in capturing long-term dependencies, we leverage the power of transformer. For the challenges in transformer-based recommendations, the ignorance of structured information, we leverage the power of positional encoding and graph neural networks. For the computational complexity of attention skills on large graphs, we utilize attention sampling and efficient sample update module. And we show that TransGNN has at least the expression ability of GNN, and any GNN can be expressed by TransGNN. And we show TransGNN can be more expressive than the first WL test. The experimental results show the effectiveness of TransGNN. That's all for my presentation. Thanks for listening.